Hello and welcome to Lesson 5, Classes in OOP, Object-Oriented Programming. Today we'll learn about classes, objects, object-oriented programming, and the two of the pillars of object-oriented programming, encapsulation and inheritance. So in our previous lessons, we've learned that variables can store data in many different forms. There's many different types of data called data types, like integers, which are whole numbers, strings, which are text values, and more complex ones like lists, which are lists of other data types, collections of other data types, or dictionaries. And the former two can be used to group of related data. But overall, variables can store data. And we've also learned that functions can act upon that data, among other things, but primarily functions can act upon data we input, and it can give us output based on that data. Usually it's a predictable output. So say we have a function called like add1, we give it 2, it gives us 3. So the function just acted upon the data we gave it. So the variables can store data, and functions can act upon that data. A class is a way of grouping together that related data and functions which act upon that data. We can use classes to model real-world objects because objects in the real world have data like objects' color or size, like a ball could be red, and behavior, how they interact with the real world. So a ball could bounce off a floor. We can model the data of the object, the properties of the object, using variables in a class, and we can model behavior by using methods, which are what we call functions, also in the class. So let's continue with the modeling real-world things analogy. So here on the left we have a balloon. It can be either inflated or deflated, and you might notice that you might start thinking that this could be represented with a Boolean value because it's a true or a false. It can be a 1 or a 0. A true or a false value is always a Boolean value. It is always a certain height above the ground, like 0 meters, 5 meters, 10 meters. This is represented with a number. And finally, depending on if it is inflated or deflated, it can rise up or down, rise up or fall down. So this one has a condition built in, it has some action built in, so this is going to be represented by a function. So previously we've used dictionaries to model real-world things. So here we can model it's inflated, we can say it's true or false, we can have a height, which is a number, but we can't really model the behavior of it rising up or falling down depending on if it's inflated. So let's see how we would translate this into Python. So this is a balloon, we could write class balloon. It can be inflated or deflated. Now looking at this function from a high level, don't really worry about the exact syntax yet, but you can see that this function seems to set this variable to true, and this function seems to set this variable to false. So we can inflate the balloon and we can deflate the balloon. It is a certain height above the ground, so this just seems to be returning some number height. So this balloon thing, this balloon class, seems to be storing this number height. And finally, depending on if it is inflated or deflated, it can rise up or fall down. There's this function here which has a condition with if it's inflated or not. If it is inflated, it's increasing height by 1. If it's not inflated, it's decreasing height by 1. So we can see a couple of functions here and a couple variables that seem to model these English properties and behaviors. The variables are modeling the properties, the data, while the functions are modeling the behavior. So on the right here we have a quick example. Before we get into the nitty-gritty, we have a quick example of how we might use these functions. So we have a variable myBalloon, which is our balloon. We can check its height. We can get its height. It seems to be 5 meters above the ground. Then we can call the rise function, and we get its height again, and it's risen to 6 meters. Then we can deflate the balloon. Which sets this variable is inflated to false. and then we can call the rise function again, and then we call, sorry, the rise method. Then we call myBalloon.getHeight, and we can see that it's descended back down to 5 meters because it's not inflated anymore. So this is the entire balloon class. And let's start breaking it down function by function. But before we do, notice that it starts with the keyword class and then the name of our class, balloon. And then the rest of all this code is all an indented block that's part of the class balloon. So the first method, the initializer, which is typed as underscore underscore init underscore underscore always. So this function's name will always be this. This is a special method, a special function. To create an instance of balloon, this method is executed with all the parameters we pass. So what the heck does that mean? So here we're creating an instance of the balloon class. So we're saying my balloon equals balloon in parentheses with some data in it. But more importantly, we're creating an instance of the balloon class and storing it in the myBalloon variable. So the myBalloon variable is an instance of the balloon class. We'll cover this concept of an instance more in depth in a second, but here we're using that same myBalloon variable. So because myBalloon is an instance of a balloon, we can call the balloon class methods on it like we see here. So here we're creating the instance of the balloon class as myBalloon. The first argument we pass it is true, and this parameter is inflated is set to true. So the balloon starts out inflated. We see that we're setting the property is inflated to true. It also starts out at a height of 5 meters because the second argument we pass is 5. The parameter starting height is set to that argument 5, and then we're setting the height property, the height variable of the balloon to 5. So again, we have this instance of the balloon named myBalloon, which can be thought of as this single balloon here. It is inflated, and we can check this by typing myBalloon.isInflated, and we can see that this is true. And we also know that it is 5 meters above the ground because that's what we started it at. And we can check this by doing myBalloon.height, which evaluates to 5. So this method is called the constructor in object-oriented programming because when we create an instance of the class, this method runs to construct our instance. To check our values of the balloon, I just showed you using this dot operator that we haven't really seen before, but this is similar to using like a key of a dictionary to access its value. So here I'm saying, in English I could say, is the balloon myBalloon inflated? But in programmer speak, this is saying, what is the value of the variable is inflated, the variable is inflated, of the balloon, this is our class, the balloon instance, myBalloon, which is the name of a variable. Because myBalloon is a balloon, myBalloon is of type balloon, and it has a variable, is inflated. Just like a dictionary can have a key and a value. So what is the value of the variable is inflated of the balloon instance, myBalloon? Similarly, we could say, how high up is the balloon myBalloon? But we could also say, what is the value of the variable height? That's the variable height of the balloon instance, myBalloon. And you might hear me say stuff like property, variable, attribute, these all mean the same thing in this context. So the rest of these are very similar to regular functions that we've learned before a couple lessons ago, and we call them methods because they belong to a class. So 1, 2, 3, 4, 5. These 5 methods are methods of the balloon class. Every instance of the balloon class will have these 5 methods. So again, here's an example using all the methods. We have our myBalloon, which is an instance of the balloon class, and therefore we can use all these methods that we've defined in the balloon class. We can check its height, which is 5 meters. We can make it rise. We can deflate it. We can inflate it. So let's break down this first function here, just as a sort of mini review and also introducing us to new concepts. So what is this self that keeps popping up in the class? When we call a method of an instance of a class, the object itself is automatically passed in as the first parameter. This way we can access the object's properties. So here we're accessing the isInflated property of the balloon. This is very similar to how we can access properties of the balloon given the name of the instance. So here we can type myBalloon.isInflated to see that it's true. We can type myBalloon.isInflated to see that it's true. Similarly, here we write self.isInflated. Am I inflated? You can think of it like that. Because the self parameter is the instance itself. That's a little bit confusing, but basically these two are the same. So here we can initialize a balloon instance using its constructor. We can say that it actually doesn't start out inflated. IsInflated starts out as false. And we can verify that here. MyBalloon.isInflated, the isInflated property of myBalloon, is false. Then we call the inflate function, and if we look here, the inflate function sets isInflated to true. And we can check this variable again. Is the isInflated variable, is the isInflated property of myBalloon, what is the value of it? It's true now. So you can see that while it started out false, because we called this function, which sets it to true, now it's true. Pretty simple. Deflate is a very similar function. It just sets it to false, so I'll skip that one. Now let's talk about get height and rise. So we've already seen multiple times that isInflated is a property or a variable of any balloon instance, but so is height, and height is a number, remember, representing its height above the ground. So all get height does is it returns a string with the height plus meters. So if the height variable here, if you look at this example, it starts out at 5 meters, and if we call get height, it just formats it nicely into 5 meters. That's all we're doing. We're returning the number and we're concatenating it to meters as a string. Again, so our balloon starts out at 5 meters, and if we do myBalloon.getHeight, we get 5 meters. Now for the rise function, we see that our balloon, myBalloon.isInflated, our balloon is inflated because it's true. So when we call the rise function, first it checks if the balloon is inflated. And so we know that this is true because we just checked it's true. So then we run this code, we increase the height by 1. So here, if we check the height after we call the rise function, it's been increased by 1. So finally, to recap, this class, balloon, models a balloon in real life because it can be inflated or deflated, and it's always a certain height above the ground. To create a single balloon, or an instance of the balloon, we use the constructor, and we can either start it out inflated or deflated. And we can also set a starting height. We can then call the inflate or deflate method of the instance to inflate it or deflate it respectively. And we can also get its height in meters at any time. Finally, we can call the rise function, the rise method, which depending on if it's inflated or not, will increase the height property or decrease the height property. A quick side note, instances are unique. So here we have a class, it doesn't really matter what's in it, but we have a dog class. And say we set the variable A to an instance to be an instance of dog and B to be an instance of dog. And so even though the thing on the right side of this equal sign, they're the same, you think these two variables are the same, they actually aren't, because they're two unique instances of the dog class. You can sort of think of this like if you had two balloons which were identical in every way. You wouldn't say they're the same object because they're two individual balloons, even though say they're both red and they're both 5 meters above the ground. This will never be true because instances are unique. So let's talk about instance attributes versus class attributes. So in the balloon example, we saw that our balloon had the two instance attributes or variables or properties, is inflated and height. This dog has two attributes, name and age. And these attributes will be unique to every instance of dog or every individual dog that we have. So here we can have a dog named Lucy, and say Lucy has the name Lucy, obviously, and she's 5 years old. We can also make a dog named Buddy, whose name is Buddy, and his age is 5 years old. And notice that we have two distinct dog objects. Kind of feels scummy calling them objects, but we're programmers. So we have two dog objects, and they have different names. This one has Lucy, and this one has Buddy. And we can have a third dog object stored in old dog, and this one can have a different name and a different age. So these three instances of the dog class, all have different names and ages, and they don't interfere with each other at all. Now this is called a class attribute. So this, you can see it's defined outside of our constructor. It's defined outside of the initializer function or the constructor. This means that it's shared among all the individual instances when they're created. So again, we have Lucy, and we can check her species, and if this annoying bar goes away, we can check its species, and you can see that it's Canis familiaris, while the name and the age are Lucy and 5. Similarly, your dog, no matter what we initialize Buddy with, his species will be Canis familiaris. An old dog, his species will be Canis familiaris. So because all dogs will have the same species, it makes sense to have this defined outside the constructor because this isn't going to be unique to every dog. Instead, it's going to be shared among the dogs. However, if we have a different dog and we set its species to something else, say Felis sylvestris, then we can change this value. We can change this value without changing it for other instances of the dog class. So while it's not technically shared among all the classes, this variable is still unique to each instance. It always starts off the same. And yeah, this would be a cat. It'd be a weird looking dog. So far we've used classes to model things intuitively that are in the real world. We could also, with this example, we can write code to simulate chemical reactions. We might use atom objects, which we can combine to create a molecule object. However, it isn't always necessary, desirable, or even possible to make all code objects perfectly analogous to their real-world counterparts. Sometimes we may create objects which don't have any kind of real-world equivalent, just because it's useful to group certain functions together. Let's practice classes. I want you at home to open up your editor and write a class called BankAccount. It should have the property balance, which is a number representing the amount of money in the account. It should also have the methods deposit and withdraw, which add and remove money from the account. Finally, it should have a method called interest, which multiplies the amount of money by 1.05. And note, I won't be checking that you did this or anything, but if you're feeling sort of shaky on this whole class thing, then this will be a really good way to check your understanding and to improve it. So here is how I want your bank account to work. So I can initialize an instance of bank account in my account. I started off with $5, so my account.balance is 5. I can deposit $10, and so 5 plus 10 is 15. I now have $15. Then it can withdraw $7, and then now I have $8 left. And finally, in my account, I can call the interest function, and then it'll multiply my $8 by 1.05 when I check the balance again. While you're trying to do this, think about why it's good to use classes for this. What would happen if we just wrote everything in a global scope, just like we just had a variable called balance and a function called interest outside of any class? Or what if we used some sort of dictionary or list? Would we be able to have multiple unique bank accounts? Would we be able to have multiple unique bank accounts existing at the same time? If you're stuck, here is the solution for the deposit method. The withdraw and interest methods should be very similar. So please try this at home, especially if you're struggling to understand this stuff. So here's my solution. Yours doesn't have to look exactly like this. You could obviously call the variables whatever you want. But here's my example, my solution to the bank account problem. So first I have the constructor, the initializer. This method up here, the init method. It only takes in one parameter from the user, which is balance, and the property balance of the bank account instance is set to that. So basically we initialize it with some money, or 0 if you're broke. Then we have the deposit and withdraw methods, which just add some number amount to the balance variable. And finally we have interest, which multiplies the balance variable by 1.05. So you might have heard me throwing around the word object a bunch. So what exactly is an object? Because we've never defined this word. Everything in Python is an object. An object has properties and methods. For example, strings have properties, their text, their length, and methods. While we haven't really looked at this, you can think of this like concatenating strings, adding strings, multiplying strings. They have properties and methods. A class is like a blueprint or a definition for our own type of object. So while there's other kinds of objects already defined in Python, like numbers, strings, lists, dictionaries, we can create our own definition for our own kind of object. In other words, a class is our very own data type, and we can create instances of this class to use it. So an analogy would be 5. The number 5 is an instance of the integer data type. It's not a perfect analogy, but it suits our needs. The string Bob or the string foo is an instance of the string data type. Just like that, our balloon, my balloon, which had the properties is inflated is true and height was 5, our my balloon was an instance of the balloon class. Or in other words, my balloon was an instance of the balloon data type that we defined. A class is our very own data type. So now that we know what an object is, we can quickly go over some ways of using them to make our programs more powerful. So here I've put some item objects in a list, and the item object is pretty simple. It has 3 properties: name, weight, and value, which are the name of the item, how much it weighs, and its value in gold or some fantasy currency. And it has a method which calculates how much or what's its value per pound, or how much gold per pound is it. And so I have my purse, and in my purse I'm storing a list of 4 items. And when I run it, you'll see that it prints out each of the items, and it prints out how much it's worth. It does this by looping through the my purse list by using the 4 item in my purse. So it's going to go through each item once, and we print out the name of the item is worth. Then we take the value per pound, turn it to a string. So the name of the item is worth its value per pound, gold per pound. So gold coin is worth 10 gold per pound. And here I've gone a step further. I've created, in addition to the item class that we looked at a second ago, I've created a new class, the purse class. And this purse class only has a single property. It's going to be a list of items. and it'll have a method to add an item, which takes in an item as a parameter and then appends it to the list. So this will add that item to the list of items. We can go through and print all the items in the list, which is using a similar for loop from earlier. We can also calculate the weight of all the items by going through each item and summing the weight. So it'll go through each item and add its weight to this sum, and at the end we'll return all the weights summed up. And similarly, we can also get the total value of the purse. And so let's just run it and see what's printing. So let me try this up. So first, our purse starts off with a gold coin, dragon hide, and a dragon tooth. And then we add the apple item right here. And as you can see, our list includes the apple at the end. Then we, and the reason they're printed is because we call the print items method on our myPurse instance, which remember is not just a simple array, but it's an instance of the purse class that we just made. And then finally we print out the get total value, and if we do this in our heads, let's see, the third parameter is the value, so 1 plus 1 plus 20, 22, 122 plus 5, 127. And yep, there we go, 127 coins total. And so the important takeaway from this is that we're using a list of objects, and we're actually using a list of objects as a property of another object. So this is just hammered in that the instances of the classes that we make are objects just like any other in Python. We can manipulate them, we can move them around, we can store them in lists, in dictionaries, all kinds of things. So what is object-oriented programming? So we've seen in our previous 4 lessons we haven't even bothered with objects, and we've created some pretty complex programs like that embedding simulator we had. So it's not compulsory to organize our code into classes when we program in Python. We can use functions by themselves, which is called procedural programming or functional programming. It's called the procedural programming approach. While a procedural style can suffice for writing short, simple programs, the object-oriented programming approach becomes much more valuable the more your program grows in size and complexity. So worst case scenario, imagine a program with hundreds of functions and hundreds of separate global variables in the same file. It'd be really difficult to maintain. All the variables could be modified by functions maybe they shouldn't be being modified by. And every time you want to make a new variable, you'd have to think of a new name that doesn't already exist, or you might end up using one that already exists and creating a massive bug in your program. It'd be really easy to confuse all these variables with each other, and it'd be difficult to see which functions use which variables because your program would be so massive. The main additional advantage of object orientation, in addition to cleaning up your code, is that it combines data with the functions that act upon that very same data into a single structure. This makes it easy for us to find related parts of our code. Since they are physically defined, they're typed out close in proximity to one another because they're in the same class. And it makes it a lot easier for us to write our code in such a way that the data inside each object is accessed as much as possible only through that object's methods. And what I just said, we'll explore that. It's called encapsulation in a second. Also, finally, some people believe that object-oriented programming is a more intuitive programming style to learn because people find it easy to reason about objects and relationships between them. In my opinion, it's a little bit difficult to take the first jump to kind of conceptualize and intuitively understand objects, but once you do, things will start clicking for you pretty quickly. And so that's why object-oriented programming is sometimes considered to be the superior approach because it allows new programmers to become proficient more quickly, but mostly because of the organizational benefits. So let's talk about encapsulation. So encapsulation is a principle of object-oriented programming. It's the idea that the data inside of an object should only be accessed through a public interface. So, for example, the balloon example, we had kept the logic for the rise method inside the class. We weren't changing the data of the balloon's height from outside the class. We would just call the rise method, and then the balloon would internally change its own data. For the BankAccount example, we kept the logic for calculating interest inside the interest method inside the class. we didn't have like a separate method, or we didn't just like do it outside of the global scope. This encapsulation is a good idea for several reasons. The functionality is defined in one place and not multiple places. It is defined in a logical place where the data is kept, so you can find it quickly and intuitively. More importantly, the data inside our object is not modified unexpectedly by external code. So this is easier to understand if you imagine collaborating with someone. Say you're writing the objects for one part of the program, and maybe they're writing some functions in some other part of the program. If you guys aren't communicating perfectly, then if he or she, your partner, just modified data directly in your objects in ways that you didn't expect, it might cause bugs that you didn't foresee. But if they only use methods that you've defined to interact with your data, that you've defined, then they can't do anything unexpected. It is usually a bad practice to modify the internal data of an object externally. We can say that the object knows how to do things with its own data, and it's a bad idea for us to access its internals and do things with the data ourselves. The second principle of object-oriented programming, and the last one we're going to talk about today, is inheritance. Going back to using real-world objects, many objects share properties. So here we have a car, we have a bus, we have a bike. They're all vehicles. So you can imagine that they all have maybe top speed as a variable. Maybe they all have current speed as a variable. And if you're writing all these three classes, you'd be repeating a lot of code. And as we've seen before with functions, a big thing in programming is to prevent repetitive code. So we can do this by writing a parent class called vehicle that describes all the bare bones of a vehicle, maybe the size, the weight, top speed, current speed, all of that stuff. And then the child classes that inherit from the vehicle class have their own specific stuff. So while a car is a vehicle, it also might have a brand, it might have a color. A bike doesn't have gas, but these two would have gas. A bus might have amount of seats, or maybe it's a double-decker bus, that would be a Boolean. Is double-decker bus true or false? So while they're all have this shared properties of the vehicle class, they're going to have unique properties like mileage or amount of seats, or even like spokes in the wheel for a bike. So here's an example for inheritance, and you can follow along with this at home. This is a really good website called W3 Schools. So here we create a class named person with the first name and last name properties and a print name method. So this is pretty standard. Here's an example. I have an instance of person in Rishi, and the first name is Rishi and the second name is not, and the print name function just prints out a concatenated string of the two names. So to create a class that inherits functionality from another class, we use the parent class as a parameter when defining the child class. So this is purely a syntax thing. We write class student person in the parentheses to signify that student is a child class of the parent class person. Student is inheriting all the properties of person. And think about this intuitively for a second. Obviously, a student is a person. A student is going to have a first name and a last name. So why shouldn't it inherit from the person class? It'll inherit all the properties and methods from the person class. And note we're using a new keyword here, pass. This just means that it just tells Python that we're just leaving it blank for now. So skip. And so here we have our class student. And right now we can use it as a person because it's inheriting from person. You can see on the right here, we can create a person named John Doe and a student named Jane Doe. And already you can see that the constructor is the same, even though we haven't defined a constructor here. It's inheriting the constructor from person. It's inheriting the constructor from person. And when we call the print name function, you see it's identical because it's inheriting the print name function from person. So what if we wanted to add properties to our student class? If we wanted to make our student class have additional info that a regular person didn't. So a student has a graduation year, right? While a regular person who's maybe graduated from their school doesn't have a graduation year. Every student will have a graduation year. So we're just adding a new parameter to our constructor. So wouldn't this work? And try this at home and see what happens. So unfortunately, this doesn't work. This is the error we get. We get student has no attribute first name when we call the rishi.printName function. So notice there was no error when we initialized the class. When we called the constructor, there was no error. But when we try to call printName, there is an error. Student object has no attribute first name. What the heck is going on? So again, the error we got is student object has no attribute first name when we called the printName function of student. So the printName function does exist because it's still inheriting from person. So why is it throwing the error? Well, you might notice that we never initialized the property rishi.firstName or rishi.lastName. So when we call the printName function and it tries to access these properties, it says, what the heck? This doesn't exist. Because in our init method, we never initialized first name or last name. Now you might say, wait a second, but in the person class, we have the init method and we do initialize first name and last name. And because student inherits from the person class, why doesn't student inherit this constructor? Well, the reason for that is because we wrote our own constructor. And this is called overriding your parent class. And we'll explore this more in a bit. But basically, if you write a method with the same name or a variable with the same name, it's going to take precedence over your parent. So Python will see this init method and run it instead, because now that we've written this, it no longer looks at person's init method. So how can we call the person's init method again? Here we're going to use something called super. So this super function allows us to access our parent. So if we call super.init, we're calling the init function of our parent class. So here we're calling super.init with the first name and last name. So again, this super function lets us access the parent class, which in this case is person. And then we can access the init function. And we're passing in first name and last name, which are set to these parameters here. And then we can define the first name and last name. So here's our full program. We have the person class that we've seen, and we have the student class. It has the init function with the super call that we just added. And so now we can have our person John Doe and our student, which now has an additional argument in its constructor, our graduation year, which is for me 2021. And we can call the printName function for both of them. And now there's no error because we've defined first name and last name because we call the init. And we can also print student.graduation year, which should be 2021 because we've set student, which is me, and we've set my graduation year to 2021. So the graduation year property of the student instance, student, is 2021. So to recap, the student class inherits all the properties and methods of the person class. However, the student class has the additional property, graduation year, that the person class does not. Also, the student class overrides the init function of the person class. This is all because the student class is a child of the parent person class, because the student class inherits from the parent person class. So we can also add methods. We've added a property graduation year, but we can also add methods to the student class. So here we're adding a new method, welcome, which says welcome, for me it would be Rishinath, to the class of 2021. So again, welcome Rishinath to the class of 2021 when we call it. And again, this is the overriding. If you add a method in the child class with the same name as a function or a method in the parent class, the inheritance of the parent method will be overridden. So inheritance review with another example. Here we have a parent class called Canis, and this is like the family of the dog, which also includes wolves and stuff. I'm not a biologist, so don't at me. But we say that we gave it the class attribute that the family is Canidae, and the init function, each instance of Canis, each wolf, is going to have a name. It's going to be a mammal, so we say it's going to be a mammal. And finally, we have this function called pet, which will say, which will cause the canine to snarl. Then we have the class dog, which inherits from Canis, meaning dog is a type of Canis, but it also has additional properties. First, we override the init function, the init method, because we want to also take in breed. So first we call the super init. We call this init function with name, so we can still define the name. And then secondly, we set the breed property. So this could be like golden retriever, for example. And then we pet the dog. So our function for pet, instead of saying snarls, it says it's happy. So this pet method is also overriding this pet method. Finally, we add a new method called fetch at the end. So let's just see how this all plays out. So we can initialize a Canis instance in wolf, and we can initialize a dog instance in dog. The Canis instance starts with the name property set to Lupus, and the dog is named Buddy, and it's a golden retriever. One of my family friends has a dog named Buddy, who's a golden retriever. Anyway, so the name of the wolf is Lupus, and the name of the dog is Buddy. So these two are the same behavior. IsMammal is the same because notice, we never defined an IsMammal function in dog. That's because we want to use the parent's IsMammal method. So we didn't need to override the IsMammal method. So when we call dog IsMammal, we see that there's no IsMammal method here. So we check the parent class, and then we see that it exists. So we run this method, and it's true. We can check the family for both of them, and we didn't override this either. So it's Canidae for both of them. Then when we call pet, Lupus snarls because he's a wolf. But then when we call dog.pet, it checks the dog class, and it sees that there's a pet function, a pet method, so it just runs this. It doesn't bother checking Canis because we've already defined pet here. We've overridden the pet function of the parent class. So we say Buddy the golden retriever is happy. And then we can also call the additional method that we defined, fetch. Buddy the golden retriever runs after the ball. All right, so practice problem number 1. Squares and rectangles. I want you to write a class modeling a colored rectangle, a rectangle with a color. It should have methods to calculate its area and perimeter. After you're done with that, I want you to write a child class that inherits from rectangle that models a square. So here's the directions. Create a new class called rectangle. It should have the numerical properties width and length and the string property color. It should have the methods get area and get perimeter. And then once you're done with these, create a new class square. It should inherit from rectangle. And remember, squares have the same width and length. So make sure your square does too. So this is how I want it to behave. So when I initialize a rectangle, I initialize it with length, width, and color. So here the length is 5, the width is 10, the color was red. And then I can get the area, it's 50, and I can get the perimeter, it's 30. This is like, it's doing math internally. So this would be like 5 times 10, and you can figure out the perimeter on yourself. And then for square, I only initialize it with side length and color because the square has 4 equal sides. And I can call all the same things. And for both of them, I'd be able to check their color. So a hint, and I'm going to give this again, but don't try to write the entire program in one go. It's easier to write a small piece and test it, and then write another small piece and test it. And always test your program with simple test inputs to see if it works properly. And when it throws an error, try to fix the error to make progress. Once you're done with the first practice problem, come back and we'll talk about the second practice problem. All right, so you're done with the first practice problem. This practice problem is going to be pretty challenging. So the libraries of small town X need a new electronic rental system, and it's up to you to build it. Small town X has 2 libraries. Each library offers many books to rent. Customers can print a list of available books, borrow books, and return books. So I'm going to provide 2 classes, book and library. It's going to be in the description of the video or in the slides, if you want to look at the slides. And they provide functionality for the book database. You must implement the missing methods to make these classes work. So part 1, we're just going to make the book. So this part's going to be somewhat simple. We create a class called book. Start by copying and pasting the skeleton I'll have in the description. This class has methods to borrow the book and return it right here and here. The class also has properties for its title and a Boolean properties to see if it's borrowed or not. However, the skeleton we provide is missing the implementations of the methods and the properties. So fill in the methods with the appropriate code. There's going to be this chunk of code at the end of the thing in the description. It's going to be testing the book class, and it should print this. If your code isn't printing this, sorry to say, it's wrong. If your code is printing this, it's working perfectly. So a hint, look at the test print statements at the end of the code to see how each of the methods are used, then fill in the code for each method. All right, part 2, the hard part. Create a class called library. Copy and paste the skeleton in the description, although the skeleton's going to be very bare bones. At the end of the program, there's going to be several test print statements just like before. All the methods and properties are missing from the library class. You will need to define and implement all the missing methods. So you're going to have to read all of these test print statements. So don't read them right now, but when you're working on the program, you're going to see all of these at the end of the program. And it should print something that looks exactly like this. So it's going to be a library class test. We're going to borrow Lord of the Rings from the first library. Then we're going to try to borrow it again, but it's already borrowed. And then when we try to borrow it from the second library, we get told it's not in the second library. So we check the books available in the first library and notice the Lord of the Rings isn't here because we borrowed it. And there's no books in the second library. We can return the Lord of the Rings and we check the books available in the first library again, and we can see the Lord of the Rings is back there. So this part is going to be pretty difficult, especially for those of you who are new to Python and new to object-oriented programming. So try to get a small part working at a time. Start by commenting the entire test section. What I mean by this is putting a hashtag before each line to turn it into a comment. This way, you can work on it one part of the problem at a time. So you can uncomment it line by line as you continue. Run the program, get the first lines working, then uncomment the next line, then get that working, etc. So again, the skeletons for both of these will be in the description. So finally, this lesson wasn't based on a textbook chapter. Instead, it was mostly stuff that I created. I also had a lot of guidance from these 4 links. So this one was the general structure of my lesson, although the content was heavily modified because we didn't talk about static methods or class methods or a lot of stuff actually. This one, W3 Schools, is always a great resource if you want interactive help online. We use that for the inheritance section. I don't exactly remember what I used this for, but I did. I think for one of my examples, I based it off of this guy's website. And finally, the library problem is a problem from the Java course at MIT, but I've translated it into Python.